All right, hello. Welcome to EEE 117. Here we're talking about Chapter 14, Intro to Frequency Selective Circuits. This is the second asynchronous lecture of the week. So last time we talked about the low pass and high pass filters. Today we're going to cover other two called band pass and band reject filters. So let's go ahead and start talking about band pass. So the idea is you will have a certain region that we can select that will pass the frequency through, called a bandpass filter or a bandpass section. We can choose the lower frequency point and the upper frequency point to kind of make a box. Anything within this box we let through. Anything outside the box we stop. Okay. So look at this Bode plot right here. You can see we have 2 points, WC1 and WC2. Okay. The passband region is in between them. So it's between the lower cutoff frequency WC1 and a higher cutoff frequency WC2. Notice that within the passband, the gain is 0 dB. So that's roughly, it just lets the voltage through, right? The gain of 1. Below WC1 or above WC2 are considered a stop band. So stop band is the frequency below the lower cutoff frequency or above the higher cutoff frequency. At this point, this is where the gain is going to be lower and can be like negative 20 dB, negative 40 dB. You're not going to get a signal. Okay, so that's the big gist of this bandpass filter is we have a middle band that we let through and everything else gets rejected. Now, big question is how can we do that? Well, we know inductors and capacitors will let high frequency and low frequency through depending on how big they are and the actual frequency of the circuit. So with a high pass filter and low pass filter, we use an inductor or a capacitor, but with a band pass filter, we can actually use both. All right. So if we put an inductor, capacitor, and a resistor in series and have the load across the resistor, we can have a RLC band pass filter. This should be RLC band pass. Okay. Now we have 3 components here. We still can do the voltage division because our output voltage is related to input voltage, except we have inductor and capacitor impedance as well. So the gain of the circuit or the voltage division is going to be the resistor divided by the impedance of the capacitor, the inductor, and the resistor all put together. You can number crunch this and massage it a little bit to where you get your S squared plus RLS plus 1 over LC. We've seen this before in the Laplace chapter, right? This is your standard RLC series circuit, right? We're just using this for a bandpass filter. So while the frequency is somewhere in the middle, there's going to be a kind of a balancing act where we're going to let the frequency through. We're going to let the signal through. Now, if you remember from one of the earlier chapters, we talked about resonance. There will be a certain frequency point where the impedance and the inductor and the impedance the impedance of the capacitor will cancel out. At that specific frequency, you'll have a series resonance where both the L and the C will cancel each other out, and then a voltage will pass straight through. And that's the whole point of a bandpass filter is we're using an RLC resonance circuit. We can select a specific frequency where the L and the C are so close to each other that they cancel out and won't let the signal through. As we get farther away from that resonant points, the impedance of the capacitor and inductor will pick up and it will lower the voltage. Okay, so that's the idea of a bandpass filter. It's using a RLC resonant circuit. Now, again, I like to talk about what happens when you have low frequency and high frequency just to double check our work to make sure the circuit actually operates. Well, remember, when you have very low frequency, the inductors are short circuit, but the capacitor is open circuit. Because the capacitor is open circuit, you just killed the voltage across the filter. So you're going to get no output voltage. You're going to get no current flowing through here. So naturally, your gain is going to be 0. Okay. And you could just plug in the math. You plug in omega equals 0, and you have 0 on the top, and then you have 1 over LC in the bottom. So you have 0 overall. Right? We could do the opposite end where we have a near infinite frequency, where we know the inductor is going to be open circuit at a very high frequency, and the capacitor is going to be short circuit. Again, because they're in series, notice that the circuit gets blocked as well. So no current is going to flow through the filter to output, so you kill the signal, which is by design, because these upper and lower extremes are outside the band, in a stop band region, so they should be attenuated. Okay, mathematically, you could take the gain of the circuit, plug in infinity everywhere, and it's going to approach zero because you have one infinity on the top, but then you have an infinity squared on the bottom, right? So an infinity squared will always go higher than a single infinity. You can even cancel them out, and you'll have 1 over infinity, which is roughly equal to 0, right? Actually, it says right here, no, right? As things go to infinity, you have infinity over infinity squared, cancel them out, 0, there you go. Okay, kind of like a little math trick we learned somewhere in calculus. Right, so the idea of inductor is open circuit and disconnects the source. So it seems like the bandpass filter works on the extreme ends. We got to just check out what's in the middle. How do we control where this resonant frequency point is, where the inductor and capacitor will cancel out? Okay. So that's the design side we're going to start looking at. Now, when we put a bandpass filter onto oscilloscope, this is kind of the output you'll see as you do a frequency sweep. Notice that you'll have 2 points that we need to design for. A lower cutoff frequency, WC1, and within this lower cutoff frequency, right, or let's just answer a question. At lower frequency, what frequency will the signal enter into passband region? So if a very low frequency will be right here, we're going to be at the stop band region. Once we hit a point where the gain is 1 over square root 2, that's that magic number, we'll then say that we're in the passband region. So once the frequency starts increasing, we'll go past this 1 over square root 2, and this middle area is considered passband region. Okay, and this lower point is called WC1, where it's officially called a lower cutoff frequency. Okay, so we're gonna have multiple frequencies to keep track of. In the low pass and the high pass filter, there was only one cutoff frequency, but here we have multiple, and this is the first one of the set. Okay, so lower cutoff frequency right here, this is where we enter the passband region. Anything below it is in the stop band region. Very important to see. Okay, we can look at WC2, right? As the frequency increases, notice the gain is pretty high, but at some point it's going to start falling off. As it starts falling off, once we cross that 1 over square root 2 threshold, we're going to enter the stop band region over here. Okay, so this WC2 is a upper cutoff frequency. Some people call it a higher cutoff frequency, right? At the higher frequency, whenever the frequency is greater than WC2, we officially enter the stop band region right here. Okay, this upper cutoff frequency that's the official name for it, denoted omega C2. So omega C1 is a lower one, omega C2 is an upper one. Okay, and those are the borders of the passband region. Okay. Now, notice that there's going to be a length between these two. We could widen WC2 and 1, we could make it skinny. We have the design parameters to widen it, right? This length of the passband frequency-wise is called the bandwidth. So we could literally say 1,000 radians per second to 2,000 radians per second, and that's the gap in between. The passband, there'll be a bandwidth. Sometimes you want a very narrow bandwidth because you only want to let a very small portion of signal through. Sometimes you want a really wide bandwidth to let a lot of signals through. That's the design parameter that you can select. Okay, the bandwidth will always be the upper cutoff frequency minus the lower one. So you could get, it should be a positive number. So you can take the difference. Okay. So far, WC1, lower cutoff frequency, WC2, upper cutoff frequency, and the gap in the middle they create, the passband, there's a bandwidth we need to keep track of. Okay. The third point is the omega 0, right? This is called a center point frequency. This is the point where we reach the absolute maximum gain of 1.0. Okay. This is also the point where we have the series resonant exactly at W0 or omega 0. Oh, that's where the capacitor and inductors completely cancel out and they have a short circuit. That's the exact series resonant point. Okay. And there's only one frequency that does that, and that's omega 0. Okay. So this center point frequency, no, it's not halfway between WC1 and WC2. It's not linear, unfortunately, right? There's a lot of quadratic forms filled into this. So a lot of mistakes people say is, if I know WC2, WC1, it's just going to be directly halfway. Unfortunately, it's not. It tends to be in a lower part of the frequency passband, right? So it might be like 40% towards the lower and then 60% away from the higher one. As you can see, it's a little tilted to the left a little bit, okay? But this is another big design component is where is that exact point that we want to have a resonance? Where is the point where we want to have the absolute maximum gain, okay? So far, bandwidth, WC1, lower cutoff frequency, upper cutoff frequency, WC2, and now we have center point frequency, omega 0. Okay. So here we could kind of just do some circuit analysis real quick to see how we could, calculate stuff. Now here we have our RLC circuit, right? This is in series. We have our output voltage across the resistor, and we got the input voltage. So the gain of the circuit is the standard voltage division, R over SL plus 1 over SC plus R. We could kind of modify it to where we get the S squared by itself, just do some algebra here. And then we take the magnitude of this and inject frequency. And this will be the gain of the circuit. It looks daunting, but realistically, all it is this S turns to JW, you throw the J away because it's magnitude only. So you have omega R over L on top. On the bottom here, this is just your real squared plus your imaginary squared. So if you plug in JW for S squared and S here, you will get a JW squared. When you square the J, it's -1. So this would be a negative W squared. And that's a real number. So it goes right here. This 1 over LC is a real number that goes over here. So to get the magnitude of a complex number, you take the real part, which is this group right here, square it, and then you add the imaginary part squared. This S right here put a JW, so this will be JWRL. This is the imaginary part, so you just square the imaginary side. And you take the square root. Okay, so plug in JW and do your magnitude calculations. It'll come up to this. Okay. Now it looks a little daunting, but remember, when we do circuit analysis, R, L, and C will be known numbers. So you'll number crunch this to like 1,000, negative, not negative, maybe 200 and 300. Just these all will be numbers. The only thing you need to plug in is your frequency, omega, right? When you want to try to find, well, what's the gain of at 5,000 radians per second? You just plug in 5,000 W, you just number crunch in the calculator and you're done, okay? So don't get too scared with variables all over the place. Okay. Now, the question is how do we relate the circuit analysis to our cutoff frequencies? Because that's what matters. Okay. I'm not going to go into detail. The math is in the book. It's like 5 pages worth of it. I don't feel like dealing with it. I doubt you do. So we'll just cut to the chase. The center frequency is where you have your resonant point. This is where the inductor and capacitor should cancel out. We saw this in like chapter 6, whenever we're talking about transformers. The resonant point of a RLC circuit will always be square root of 1 over LC. So right here, if you know L and C, you can find your center point frequency. Additionally, you can find your center point frequency by taking a square root of WC1 squared times WC2. Okay. It's kind of like a math trick. I don't know exact math trick, but there's like some geometric average, whatever math trick. So either one of these you can use. WC1 and WC2, they just solved for 1 over square root 2. I think it's a quadratic form. That's why this kind of looks like negative b squared plus or minus square root, blah, 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 right? So to find your center point, your lower cutoff frequency is negative R over 2L plus square root of this. Find your upper cutoff frequency, it's positive, said negative R over 2L plus everything in the square root. Okay. I don't expect you to derive this. I would just literally have this chart on the side just to number crunch when needed. Okay. But the big trick here is every frequency parameter can be figured out by R, L, and C. Right. So either R, L, and C, you can figure out cutoff frequencies, or you have cutoff frequencies 1, 2, 3, and you need to figure out R, L, and C. You could do either one of these. Okay. We're going to do a couple examples just to show you the number crunch. Don't worry. Okay. Another thing we need to design is the bandwidth. The bandwidth can easily be found by the upper cutoff frequency, omega C2, minus the lower cutoff frequency, omega C1. That's the obvious one. Mathematically, you could play around, and you can also find out that the bandwidth is equal to R over L as well. So that's just another equation you could use in your toolkit to design bandpass filters. Okay. Again, I want to emphasize your center point frequency is not dead center between bandwidth, right? If people think if your bandwidth is 3,000 wide, your center frequency is halfway between the bandwidth, it's not. Remember, it typically tends to the lower half. So it's a very big thing people get wrong on a lot of times is they just take the bandwidth, cut it in half, and that's your center point frequency. That's wrong. It's not, okay? Even though it says center, which I don't like the name center point, it's because it's not center, but that's what we've chosen, unfortunately, okay? After designing it, some people came back and said that the filter it's too flat sometimes, it's too spiky, right? Like you saw in the previous graph, one was kind of flat, one kind of made a pretty big dip and came down. So there's different arguments you could be said that maybe we want a flat one, maybe we want a very spiky one, right? So there's another quantity we could play with called a quality factor Q. Quality factor Q is basically how sharp of a rise do you want your bandpass filter to be. Do you want it to be very wide and flat? Then go for a very low Q. If you want to be very narrow but very spiky, so you have a very small band, but it's very, very sharp gain, then you want a high quality factor Q. So think about it just a way you could play with the output, the graph. You can make it flat and wide, you can make it skinny and very high. Okay, it's just another part of the circuit design. Okay. So Q factor, the higher the Q will make the passband more narrow and defined. Lower Q makes the passband more broad and flat. Okay. So if you want a very wide breadth, go for low quality factor. If you want a very narrow, accurate pinpoint filter, go for a very relatively high quality factor. Okay, and here's kind of a graph to show you. You could go quality factor all the way from 0.5 to about 10. I've seen 50 before. That's pretty crazy though. But that's just, again, another circuit parameter. Whenever you get to your later courses, you need to design a filter. You at least know how to do it now, okay? So we have 5 things we look at. Quality factor Q, bandwidth beta, lower cutoff frequency WC1, upper cutoff frequency WC2, right? And then your center point W0, right? Or I should be saying omega, not W, but let's go ahead and do an example for a series RLC bandpass filter. So notice you have the circuit, the inductor, capacitor, and resistor, output voltage across the resistor. Design bandpass filter with a lower cutoff frequency of 5,000 radians per second, an upper cutoff frequency of 15,000 radians per second. Between these two, you know your bandwidth is 10,000 radians a second. Given that we want the resistor of the circuit to be 10 kilo ohms. Okay, well, we got enough information, we could just plug and chug this. Okay, first the bandwidth, we know resistor, so B equals R over L. That's a very easy calculation. L is just 1 Henry. So we already checked that off. Okay, so remember we want R, which is given. We need L and C. We just figure L. L is 1 Henry right here. Now we got to figure out capacitor. Now I would strongly suggest just have a list of all those equations. You just like 7 of them, and just use whichever one's most convenient. Right? There's no one way to do it. The way I did it is I said, well, I know WC1 and know WC2. I can find my center point frequency. Right? So omega 0 is just square root of omega C1 times omega C2, which is 5K times 15K square root, and it's 8.66K radians per second. Okay. We could then take that, and this is just the second page to keep doing the work. And with our center point frequency, we know we can hit that resonant point where omega 0 equals square root of 1 over LC. Well, we could take the square root off by squaring both sides. So we have omega 0 squared equals 1 over LC. swap the C around with the omega 0 squared. So you get C equals 1 over omega 0 squared times L. Just plug in some numbers in, and you get C equals 13.3 nanofarads. Okay, so design spec here is resistors 10 kilo ohms, inductors 1 Henry, capacitors 13.3 nanofarad, and there you go. Now you have your filter built. Okay, so it's just a matter of getting used to the equations. No one says you have to memorize them. Like I said, have a sheet of paper nearby with them, and just play around with some algebra until you find the right answer. Okay, there's lots of components in this filter, lots of building blocks, but after a couple of times, you'll get used to it. Okay. Honestly, if I were you so inclined, you could just make an Excel sheet and pre-program it. That way, you just do a lot of work once, you could just keep using it over and over again. That's up to you. So here's a good chance to practice that. So here we're going to take a 15-20 minute break where you will design an RLC bandpass filter, very similar to what we just did, except the different design parameters. So a lower cutoff frequency of 2,000 radians per second, upper cutoff frequency of 8,000 radians per second, right? We got resistance of R equals 10 kilo ohms. Give me the L and the C to make this happen. Design the filter. Okay. So you got 2 pages to fill everything out. Fill out the L and C right here, and we'll come back and check your answers. Okay. So again, 15-20 minute break, and we'll come back and resume. So see you guys in a second. Hello, welcome back to EEE 117, Chapter 14, Intro to Frequency Selective Circuits. We're coming back from our break for the series RLC bandpass filter design. So let's go ahead and check your answers, see how we do it. So remember, lower cutoff frequency is 2,000, upper cutoff frequency is 8,000. We could just figure out the bandwidth first off. It's always the upper minus the lower, so it's 8,000 minus 2,000. So our bandwidth is 6,000 radians per second. So that's the bandwidth in between the 2 points. Now we have the bandwidth, we already have a resistor given to us. So we can just do some basic algebra to find out the inductance L is 1.67 Henry so far. Okay, so we have the L, we have the R already, we need to figure out the C. So the next thing I do is I find the center frequency, that's just square root of lower cutoff frequency times upper cutoff frequency, which is 2,000 times 8,000, 2,000 right here, 8,000 right here. Multiply them together, square root them, and our cutoff frequency or center point frequency is 4,000 radians per second. Again, that's a frequency where we want to have the exact resonant point where the inductor and capacitor cancel out. You can figure out the resonant point by setting the center frequency equal to a square root of 1 over LC, where we just do some basic algebra, cancel some square roots out, and we have capacitance is equal to right here 1 over center frequency squared times L. Plug in some number where center point frequency is 4,000 squared times inductance of 1.67 Henrys. So 1 over 4,000 squared times 1.67, and we get 37.4 nanofarads. Okay, so end results of design are 3 components. R is 10K, L is 1.67 Henrys, and capacitor is 37.4 nanofarads. Okay, so it's just a matter of getting used to the equations, figuring out which ones you need, and you could go through and design these filters, right? There's obviously homework problems. You could see different variations of this from different angles and whatnot. Okay, so that was a band pass filter. We're going to now talk about the band reject filter, which is kind of the quote opposite of it, where we'll have a band in the middle, except it's a stop band this time. So we still have our lower cutoff frequency, our upper cutoff frequency, but everything in between those 2 flagpoles, right? That middle ground, that's going to be the cutoff region, the stop band. Everything below the lower cutoff frequency and above the upper cutoff frequencies, those extreme ends, that's going to be the pass band that we let through. Okay. So stop band is between lower cutoff frequency WC1 and higher cutoff frequency WC2. It's here and here. Okay. Pass band frequency is any frequencies from 0 up to the lower cutoff frequency, so all this area. Passband is also from cutoff frequency to upper cutoff frequency and onwards to all as high frequency as you can go. Okay, so you're kind of just carving out a little center area and says, nope, we're blocking that. Everything else we'll just let through. Okay. Circuit wise, it's because it's literally doing the exact opposite. the easiest thing is to take the RLC circuit that we've been using and take the output voltage and just swap it over to inductor and capacitor. Previously, this was across a resistor. We're just swapping the voltage around, right? So that the output voltage will have a ratio somewhere in the middle, right? Where so this inductor capacitor would tend to cancel each other out. Because remember, inductor has positive impedance, capacitors have negative impedances. We can actually figure out exact point, that resonant point where the inductor and capacitors cancel out. If the inductor and capacitor cancel out, there's a short circuit here, right? Then your output voltage is zero. So your output voltage is across the resonant capacitor and inductor, so that middle area is going to naturally cancel out, right? You're short circuiting the output, so nothing's going to come through, okay? Now, at the very lowest, oh, and then the gain of the circuit is output voltage compared to input voltage, where we're doing the resistor voltage division, except we're across inductor capacitors time. So you can just do the math here, right? You're going to have the inductor impedance plus the capacitor impedance divided by all three impedances put together. We could just do some number crunching around just to make things look nicer. At the very, very lowest frequency, near zero, we could check there should be a pass band. Well, let's look. At the very lowest frequency, the inductors are short circuit, but the capacitors open circuit. So meaning this point right here, there'll be no current flowing through it. It's going to go to the rest of the load. Okay, so remember, output voltage is connected to the next circuit. So in essence, the current will flow straight through and it's not going to get shorted. Because remember, in the middle area, the voltage gets shorted by inductor capacitor, but the capacitor is open circuit, so we get the highest voltage possible right here. Okay, which is what we want. When we have a very high frequency near infinity, the same thing will happen, except the inductor is now open circuit and the capacitor short circuit. We're letting all the voltage through, and thus we're at the pass band as well. Okay. And of course, you can plug in zero right here. You have zero squared plus something. Doesn't matter what's on top. And you have a 1 over LC, so we're not divided by zero, so your gain is 1. Right? When we plug in omega equals infinity, we add infinity squared, divide by infinity squared, nothing else matters. So infinity squared over infinity squared is roughly equal to 1. So the math checks out. Okay. So at the end of the day, is the main difference here is you're taking voltage across inductor capacitor for your band reject filter. Okay. Now, in terms of what your output will look like if you have oscilloscope, you can do a frequency sweep. You'll have your lower cutoff frequency, WC1, right? Where any signal with a frequency from 0 up until this point is going to be pass band. It's going to have a very high gain of 1 down to 1 over square root 2. Once we pass that gain of 1 over square root 2, we officially enter the stop band region. Okay. So what lower frequencies will frequency, what frequency will the signal enter the stop band? When the frequency reaches this lower cutoff frequency, omega C1. Okay, that is the border where we enter the stop band region. Okay. As we go through stop band region, notice the gain will eventually go to 0. And this point right here is our resonant point. This is where the inductor capacitor fully cancel out. So you short the output. That's why it's 0 volts. And the gain is 0. And then the gain will increase up to 1 over square root 2 as we get away from the resonant point. Okay. So as the frequency gets higher, the inductor impedance gets bigger, and then our gain starts building. Okay. So here, this point is let's read it. At a high frequency, what frequency signal will exit the stop band region? So as our signal gets higher frequency, our gain's better, it gets better and better. Once we get past that 1 over square root 2 gain, we're now considering the pass band region. Okay, and that frequency point where we start entering the pass band region is called our upper cutoff frequency, WC2. So it's the same terminology as the band pass filter, except I like to think of that the gain is kind of inverted. Remember, the band pass filter was flat and went up and then down and flat. This is the opposite, where it's high and then it gets a valley and then it goes high again. So they're kind of opposites. Okay. We still have the same bandwidth, except the bandwidth this time is how wide is the stop band. And the bandwidth can be figured out from the distance between WC1 and WC2, where mathematically you could figure out by calculating the upper cutoff frequency minus lower cutoff frequency. So again, the bandwidth is how wide do you want that stop band to be? You want a very narrow stop band, very low bandwidth. You want to have a very wide stop band to stop a lot of things, have a very wide bandwidth. That's a design parameter you can play around with. Okay. You also have the center cutoff, the center point frequency as well, omega 0. This is where the inductor capacitor completely cancels out. And when you short out the output, you get 0 volts. You get no gain, which makes sense because you're shorting the output. Okay. There's only one point at one frequency this will happen. Again, it's a center point frequency called omega 0. Just like before, omega 0 is not dead center between WC1 and WC2. It's kind of offset a little bit to the lower frequency side. So notice like it's a little closer to WC1 than it is to WC2. So don't just take the average of these two and just assume it's W01, omega 1, right? That's one of the biggest mistakes I see people do in these calculations. Okay. Circuit-wise, we could go ahead and look at the output. Your output voltage across inductor capacitor. Here's your gain function we've seen before. Take the magnitude. It's the same idea, except the top part's a little bit different. You're going to have omega JW plugged into S, so you can have JW squared. So that's a negative W squared plus 1 over LC. So you take the magnitude of 1 over LC minus omega squared. Right? So that's where this came from. The bottom part is the same real and imaginary calculations we did before. We take the real part square plus imaginary part square root. So it's just figuring out the magnitude. That's it. Okay. Now here's the fun part. That makes it at least easy. Remember, we have 3 frequencies we need to keep track of. Center point, lower cutoff frequency, upper cutoff frequency. Because this is still the exact same circuit as a bandpass filter. It is. The only difference is we're taking the output voltage across inductor and capacitor, right? All your equations are exactly the same. It's the same circuit. Nothing's actually changed. Well, the only thing that changed is your output voltage. Remember, for a band pass filter, the output voltage is across a resistor. For a band reject filter, the output is across inductor and capacitor. So component-wise, nothing's changed. You're just taking the output wires and plugging them in different points of the circuit. Okay, so the natural behavior of the circuits, the way the electrons flow, that hasn't changed. You're just plugging in the output terminals in different places. So because the circuit hasn't really been altered, all your equations are exactly the same. So that's the one saving grace about bandpass and band reject filters. They're pretty much the exact same design, except you just got to make sure you know if you want a band pass or band reject. That's the only difference. Okay, so center point frequency is still 1 over LC, square root of 1 over LC, or you could take omega lower cutoff frequency, omega C1 times upper cutoff frequency, omega C2, square root both of those, and that's your center point frequency. Lower cutoff frequency, upper cutoff frequency still could be figured out by number cruncher R, L, and C here, right? Same thing with your bandpass filter. I mean, your bandpass or bandwidth is upper cutoff frequency minus lower cutoff frequency. You can also find it as a bandwidth equal to R over L. Okay. Remember, center point frequency is not dead center between the bandwidth. It's kind of closer to the lower end of it. Okay, so don't just take the bandwidth, cut it, divide by 2, and say it's a center point frequency. Again, that's a very common design error to see. Okay. Here, same thing with a quality factor, exact same as a bandpass filter, is square root of L over R squared C, right? I can put it right here, band reject filter. Oops. Band reject filter, there we go. Okay. So here, the quality factor, remember, a higher Q will make the stop band more narrow, and a lower Q will make the stop band bigger, right? So technically, I should probably, this should be stop band, not pass band. Okay, let's see if I could. Stop band like that. And stop band. Okay. There we go. That should sum everything up. Okay. So here's a good example of the band reject filter. Is you'll have the band reject filter with a cutoff frequency of 5,000, the lower cutoff frequency 5,000, upper cutoff frequency of 15,000. The bandwidth is 1,000, resistance is 10 kilo ohms. This is actually the same numbers as a band pass filter, except notice that just the output voltage is different. We're going to do the calculation again, but honestly, it's the same. I mean, I did this on purpose because I want to show you that the calculations are the same for a band pass versus a band reject filter. Okay. So bandwidth is R over L. Just swap L and bandwidth around. So you got L equals 10K over 10K, which is 1 Henry. Center point frequency is square root of lower cutoff frequency times the upper cutoff frequency, which is 5K times 50K, square root that. Center point is 8.66K radians per second. Okay. Then we could find the reject filter. Also fix everything where we're at it. Okay. So same numbers. Now we got to find the capacitor. So we have a center port frequency equals square root of 1 over LC. Just kind of do some algebra. You eventually find C is equal to 1 over omega 0 squared times L. We just plug in omega 0 and L. 8,660 squared times 1. Capacitor is 13.3 nanofarads. Okay, note that these are the same numbers for bandpass filter. The only difference is that V out is in the different spot. Okay, so that's one of the kind of nice things is if you design a bandpass filter, you can actually have the band reject filter right then and there if you need it as well. So it's one circuit that does both things. Just a matter of which function do you want today. Okay. So kind of just a summary of band pass and band reject filter side by side. So remember, a band pass filter is the same RLC circuit except output voltage across a resistor. Band reject filter, it's the same circuit except the voltage across the capacitor and inductor. It can't be one or either, it has to be both. Okay. Because it is the same circuits, all of your calculations and design parameters are the same. So lower cutoff frequency, upper cutoff frequency. Here you could calculate if you have RLC. You got center point frequency here. You got your bandwidth and quality factor. So remember, there's always 5 things to design. Lower cutoff frequency, upper cutoff frequency, center point frequency, bandwidth, and quality factor. Those are the 5 parameters you're going to see with any band pass and band reject filter you design in the future. Okay. So that's about all I have for today. Hopefully we made the math a little more easier to understand and you get more the conceptual idea of how a bandpass filter works. Because as you go into your next couple courses, these things will only get more complicated as you add more complexity to it. But again, it's always good to have some basics so you know what you're getting into. Okay. So thanks for showing up. Thanks for paying attention this week. Hope you guys have a good rest of the week and we'll always be here for next week for a new topic. So you guys have a good day. See you around.